And so it's a pleasure to have Jiri Rosicky speaking about injectivity and metric enriched categories with his joint work with Jiri at. So feel free to start when you're ready, Jiri.
Yes. So this is what we did with Jirka during spring lockdown. So having plenty of free time. So math is the category of generalized metric spaces. It means that we also admit distances infinity. So 2 points can also have distance infinity. And non-expanding map, it means that maps which cannot increase distance. So distance of the images is less or equal to the distance of the points. The reason why one takes these generalized metric spaces is that having usual metric spaces, for instance, you don't have coproducts. Even you don't have a coproduct of 2 points because you have 2 points, so you have to put some distance to them, and you cannot do this distance should be arbitrarily large because you can have any distance between 2 points, and this coproduct should have non-expanding map to any possible distance. The same thing is that with infinite products, it forces you, this projection forces you to have also infinity distance to have products. So this is more advantageous to work with these metric spaces, which are, I think, somewhat propagated by Bill O'Weir in this famous paper. And CMAT, this is full subcategory consisting of complete metric spaces. So this is where the situation where we are living. So both categories are nice. So they are locally R1 presentable and symmetric monoidal closed. So tensor product is Cartesian product with the plus metric. Just I remind you that on Cartesian product, on categorical product, one has maximum metric or submetric if you want. Lambda presentable objects are objects having cardinality smaller than lambda, which is lambda uncountable. In metric spaces, in complete metric spaces, one doesn't count cardinals unlike sets, but density characters. It means this is the maximum cardinality. This is the smallest cardinality of dense subsets. So, for instance, I'll have one presentable objects in collimetric spaces are separable spaces having countable dense subset. One has to take uncountable because our zero presentable objects are is the only empty space. That's a kind of easy argument. So one has to take this lambda at least L1. So this is the basic situation, and now we work in metric enriched categories, which appear in many areas. Just I here mentioned 2. So one is so-called continuous logic. So this is the logic over metric spaces. For instance, it emerges from functional analysis. Or quantitative algebra, these are algebras over metric spaces. Again, they are motivated by probabilistic programming. So there are also some other motivations for look at these metric enriched categories, both in computer science and in analysis. And one prominent enriched category are Banach spaces. So Banach spaces, and again, one has non-expanding things, so linear maps of norm at most one. So these are categories I will need. And this is now the basic concept that one has 2 morphisms in such metric enriched category. And one can say that these morphisms are epsilon closed, which means that their distance Of course, this is the distance in this metric space of morphism from A to B is not equal to epsilon. This makes possible to speak about epsilon commutativities. It means the diagrams commute not strictly, but commute up to epsilon, which means that both legs are of distance small equal to epsilon. And in some sense, one, that was it somewhat, but the point here that one does something one is used to do with usual categories, one does it up to epsilon in this sense. In some sense, it might resemble somebody that's something like homotopies. But now these homotopies somewhat are not transitive, because if two morphisms have this strength, are epsilon close, to other one are delta close, so the first and the third are epsilon plus delta close. So these homotopies are not transitive. But this is just an analogy which I just wanted to mention it. So now the basic definition. So you have a morphism, you have object, and you say that the object is epsilon injective to F. If having any morphism G from A to K, so that X is always H, such that HF is epsilon close to G. So this is natural, but the really right concept is approximate injectivity. It means that it's epsilon injective for every epsilon. So whenever I choose epsilon and I choose G, so I can find arbitrarily for any epsilon greater than 0, I can find such approximations H. So this approximation in some sense are converging to real injectivity, but one doesn't get it. Of course, if K is injective to F, so this approximately injective to F because I take this real factorization and distance is 0 because they're equal. Yeah, so this injectivity is stronger than approximate injectivity. And why one does it? So this is motivating example. So one takes Banach spaces and one looks at isometries between finite dimensional Banach spaces. And one looks to injectivity with those isometries. This is the most natural thing to do. And that's known that no separable Banach space is injective to those isometries. But there is a separable Banach space which is approximately injective to these isometries. And even more, this space is not only approximately injective, but also approximately saturated. So this saturated, this is considered a model theory. And what's the difference here? So I work with isometries. That's like embeddings in model theory. So now I take this F, this is embedding this isometry. Now I take G, which is isometry again, but just from injectivity, I don't know this H is isometry. So also from, say, approximate injectivity, I don't know this H is isometry as well. So this is stronger to be absolutely saturated. Yeah, so it's written here that if these isometries, so H is isometry 2, or one can find isometry that's broken. And like saturated objects, these apparently saturated objects have, so usual saturated objects are usually determined. So in usual situation, if you have morphisms between finely presentable objects, so object which is saturated and is one presentable is unique up to isomorphism. So something similar is here as well, because this Banach space, which is approximately injective and separable, is even approximately saturated. And it is unique up to isomorphism, which is not so clear. I will come to it at the end of my talk. But this space is called Gurari space. Then I will take at the end some history about these spaces. So this is why one somewhat is forced or motivated to do this approximate injectivity in Banach spaces, because it behaves better. You have this nice space which is approximately injective, but you don't have a nice space which is injective. So this is a kind of motivation. Also, that this terminology came from functional analysis, is approximate injectivity. This Walter Tolle, this is this T here, some years ago, we started to look at it from the point of view of category theory to this phenomena, so enriched category theory. And now this work with Adamek is a continuation and further development of these. So this is a definition of isometry in any metric enriched category, not just in Banach spaces. So in every metric enriched category, so the difference is here. So for any pair UV which goes to K, the distance of composition is the same as distance of U and V. And isometries in metric or Banach spaces are precisely those abstractly defined isometries. So dually, co-isometry is that you have a dually. So co-isometry is isometry in dual category. So for any two outgoing morphisms, you have the same distances here. So in these categories, isometries have usual meaning. So it's isometries. And co-isometries are dense morphisms. It means the closure of image is the whole codomain. Now, the first important fact is that if the category K has conical limits, this is in the sense of enriched category theory, it means that this underlying category has limits which are preserved by enriched Hom functors. So, and this underlying is well powered, so then isometries form a right part of an operation system. And dually, with conical colimits and co-well power, co-isometries form a left part of the operation system. So on good metric categories, one has two factorization systems. So for instance, in metric spaces, you have surjective isometry and co-isometry, closed isometry. You take just image and embed it. Here you take image, find closure, and you get closed isometry here. But in complete situations, it is complete metrics of Banach spaces, they coincide. And you just get co-isometry, isometry factorization system. Just not to believe that these isometries are too strong. So take ordinary category, which is treated as enriched. It means that, well, maybe I should tell it at the beginning, because any discrete space is metric, because you can take distances between 2 points infinity. So in fact, this is left adjoint from sets to those generalized metric spaces. Take a set this distance infinity. So any category can be understood as enriched discretely, and then just isometries are just monos, that's here because the only distance is 0 here, except infinity, of course, and co-isometry is epi. Yes, so it corresponds in some sense to monos and epis in some sense, yes. So this is the first thing which somewhat puts this, say, analytical concepts of approximate injectivity to enriched concept. So if our category is enriched, but that's important, our complete metric spaces. So to be approximate injective is the same with these induced morphisms. The usual induced morphism you get here is co-isometry. It's easy to see it. Just let me come back here, because it means that these approximations are dense in some sense, they're arbitrarily close. So just a moment's reflection gives you that this injectivity is like enriched injectivity, because in the terminology of my paper with Steve Ladd, in this, we had some base, some minimal closed category with some chosen class of morphisms, say, for E. And now one speaks about E-injectivity, which means that this morphism belongs to E. So, of course, if you choose as this class the isomorphisms, you get orthogonality. If you choose over sets these classes epimorphisms, you take usual injectivity. So now, if you take now this class of isometry, so then this is E-injective to this class. So this is the first observation that the enriched category theory can supply this kind of analytic definition of having arbitrary close approximations. You are replaced by category theory concept. So now one wants to try to do everything what one does with usual injectivity. So one has a class of morphisms, and one takes F triangle is the class of all objects which are approximately injective to every F of this class. And this black triangle, one takes class which are injective to this class. On the other side, having a class of objects, so this triangle L means the class of all morphisms such that any object from L is approximately injective to F. And the same is this black triangle. And what I told you that injective implies approximately injective, it means that this black triangle is more equal to triangle. So this is just terminology. Now one knows what are typical properties of these classes of morphisms to which given objects are injective. So this is always left cancelable. This is evident if you have a composition of two and an object is injective to composition, so to the first one, this is just immediately visible. And that's well known as closed under push-outs and transmit compositions. So one would like to know what is true for this approximate injectivity. So the first thing is that cancelable is replaced by approximately cancelable, which you have described here. Which means that if you have given a morphism in this class, and you have another morphism, say for any epsilon, that's this epsilon factorization, so it belongs to this class as well. So in particular, it's left cancelable because this is more general because it's left cancelable, so then you have it immediately. So now to get some of this analogy of push-out, so one needs a new concept which we introduced that in result of Tolle in that paper, and it was an epsilon push-out. So you have two morphisms, F and G, and now epsilon push-out is epsilon commutative square. It means that it comes up to epsilon. So then for any other epsilon commutative square, that's a unique morphism from D to D prime, but now this is strict, now this commutativity. Yes, so at the beginning, it looks like a kind of delicate game. So where you have to put epsilons and where you have to put equality. Yeah, so this is the right definition of an epsilon push-out. I will say more about it later. And the fact, which is again immediately visible, is that if you have epsilon push-out and this F is such that it's in triangle of class of object, so this bar, F bar, is in black triangle. It's because if you have for any morphism here, you have epsilon factorization, so then you just, for morphism here, you have morphism, so it means that you have this composition, so epsilon factorization, so due to epsilon push-outs, you get strict factorization. So just immediately from this definition that one has epsilons here and equalities here, one gets that push-outs of things which are approximately injective are strictly injective to class of objects. But mind,
Hello?
sorry.
Hello?
Yeah, and the consequence then is that this triangle L, sorry, a question or something? This triangle of L is closed under transient composition of epsilon pushouts. Why? Because if you take epsilon pushouts, you go from triangles to black triangles, and those black triangles, it means injectivity is closed under transient compositions. So one gets a kind of closure property of this class, triangle L. But just I warn you that it doesn't mean that this class is closed under transient compositions. I don't claim it. I don't claim it because if you take push out of morphism alloc identity, epsilon push out, so this is not a push out. So in fact, this doesn't mean that this D is B for epsilon push out. Yeah, so if something is closed under epsilon push out, it doesn't mean it's closed under transient compositions. Well, in fact, it's not an interesting question probably whether it's closed under transient compositions. One can show it's closed under composition of 2 because you want to get factorization up to epsilon. So you did it under epsilon half and epsilon half, so did under epsilon. Even if you have countable transient composition, you can do the same thing by expressing epsilon as a sum of geometric series. But I don't think that it's closed under uncountable compositions. But what's important is this fact. And now just terminology. So one has this class F, and I close it under those transient compositions of epsilon pushouts. Of course, epsilon is a variable here, and I denote it as approximate cellular morphisms. So in fact, in some sense, you have a class of morphisms. You take objects which are approximately injective to them. You take back those morphisms which are such that these objects are approximately to those morphisms. So this is a kind of a theory. You take all consequences of F, and then one gets into these approximately cellular morphisms. So that's one thing. To understand what happens with this relation between morphisms and objects and this relation with approximate injectivity. This is the same thing one has to analyze if one does classical injectivity. Another thing is that we would like to do something like approximate small object argument. We would like to know that this construction you get to obtain this approximate object somewhat converges. So one needs an analogy of the fact that object is lambda small, and this is approximate lambda smallness. So what does it mean? So you have a class F again, and now you look at lambda directed transient compositions. This is as in the classical case of morphisms which are approximately cellular to F. And now your object is approximately lambda small if for any epsilon, so any morphism from A to the colimit of this, you see this composition, you have also its colimit. So it has epsilon factorizations through something on the way. That's like with injectivity. Any morphism to colimit factorizes through something. So you have this epsilon factorizes. But one has to be a little bit careful how to formulate this essentially uniqueness. So in this one, so if you have two morphisms from A to Ki, such that their morphisms composed with morphisms to colimit, this is epsilon close. So then it is epsilon close if you compose it with something in this diagram. So this is approximate smallness. And why it's natural is that if you are again enriched or complementary spaces, so then approximate lambda smallness with respect to f is the same thing at this home functor preserves lambda transform compositions of approximately cellular morphisms for f. So you see these two conditions in some sense exactly describes, say, this directed colimit in complementary spaces. So again, a little bit of thinking tells you that this abstract description, which is the right thing how you would like to define it, of course, from enriched category theory point of view. So this is this concrete description which you have here. Yes, so these are in fact two observations which we did with Jiri Rosicky, that you can replace approximate injectivity by enriched concept, and you can replace this approximate smallness by enriched concept. And then this is the result. So again, you can compare it with the known situation of injectivity. So we have some plasmomorphisms, but their domains are approximately small, which means I haven't wrote it down. It means that approximately small is approximately lambda small for some lambda. Then this class of object approximately injected to F is weak reflective, and these weak reflections are approximately cellular. So this is just that you run this model argument by taking epsilon push-outs and transforming compositions. It stops during this assumption of approximate smallness, and what you get is weak reflection, which is approximately cellular by its construction. And moreover, if you now go back, so if you take F, if you take this approximate injective, you take again morphisms, you take some of the closure of F under this situation. So then it coincides with approximately cancelable closure of cellular morphisms. So this is again analogy with the situation with injectivity, which varies here in general. Of course, something which I have to address immediately is that for all that I need the existence of some colimits. I need transform compositions, but I need those epsilon push-outs which are not so clear. So one should know that in categories I'm interested at, in Banach spaces, one has epsilon push-outs. So, but I will come to it in a moment. But with this, having this available, so then you have this, the first fact, which somewhat gives you understanding of this approximate injectivity. So to understand better what are epsilon push-outs, so one has to remember weighted limits and weighted colimits. So I have a diagram, and I want to see what is colimit weighted by this weight. This colimit, so this contravariant, so this weight is cospan. And just a little bit of thinking tells you that this is precisely epsilon push-out, but such that these two morphisms are jointly coisometric, which means that whenever you have a pair of two morphisms outgoing from D, so their distance, so it means that if you take coproduct of B and C and take the induced morphism by F bar and G bar, so this should be coisometric. So this distance of two morphisms is the same as the distance by compositions with this induced morphism. Yes, so to be weighted colimit, it's more than epsilon push-outs. You need this epsilon push-out is coisometric in this sense, which is natural again, because in this epsilon, this is quite clear, because then I will show you how this epsilon push-outs look like in metric spaces. That one, in usual push-out, what you do, you identify points FA and so A is small now, FA and GA in coproduct. Let's push out. In epsilon push out, you don't identify them, but you put distance epsilon to them. Or you want to put distance epsilon to them. But for weighted collimate, you also need not only that these sets are the same, that these metric spaces are the same. So this is coisometric condition. That the distances in this, say, metric space from D to some morphism correspond to what is there. So this is the right description of weighted collimate and which are coisometric epsilon pushouts. And in some sense, whenever you have coisometric epsilon pushouts and dually isometric epsilon pullbacks for all epsilons, so, and if your underlying category is complete and co-complete, then your category K has weighted limits and colimits. So in some sense, one can say that is epsilon pushout, but one has to combine both to get it, yes. There is epsilon pushout isometric and pullback isometric. The existence plus completeness on a category is the same, that there's no weighted limits and colimits. So why it's true? Yes, that's of course, whenever your category K0, K0 has limits and colimits, so what you need for weighted limits and colimits? You need that those things are conical, but also you need that you have cotensors and tensors. And the point is here that the tensor is, so tensor epsilon pushouts. So tensor, what's a tensor? You take metric space, you take object in your enriched category. So tensor is this thing, and the same thing as epsilon pushouts along identities. Of course, now I don't have all tensors, but every metric space is a colimit of 2 epsilons, because just I put this distances to points, which means that I put 2 epsilon there. And tensor of a colimit is cotensor of colimit of tensor, so one get this thing as a colimit of epsilon pushouts. So this is why colimits and epsilon pushouts give that. So this is quite strong conditions to epsilon pushouts. And now you see this is their description. So in metric spaces, you take coproduct, and you take the change distances from infinity, because in a coproduct, 1 point here, distance infinity. So you take it to epsilon, but then you don't know that you get metric space, because you need triangle inequality. So you force it. So you generate metric to force triangle inequality. It can be done. So this is a description of epsilon pushouts. Epsilon pullbacks are easier, because just you take product and you take subspace of all pairs that have distance small equal to epsilon. Usual pullback has, in fact, those which belong to both. So here, just instead of distance 0, I have distance small equal to epsilon. So this is epsilon pullback in metric spaces. Good. So this is a kind of preparations. This theory, say, done for enriched categories. And now I would like to look to this motivating situation, so to Banach spaces. So Banach spaces, it's again locally relevant presentable category. This is well known. And as a forgetful functor, one has to take unit ball functor. I have to send to the Banach space only the unit ball. So only have a distance less or equal to 1 from 0. And this is because otherwise, usual forgetful functor doesn't preserve limits. So one has the unit ball functor which preserves limits and relevant directed colimits. In fact, it even preserves directed colimits. And just that's enough to show that it is left at the joint, because both categories are locally presentable. This functor is with a limits and is accessible. So one has left adjoint. By the way, these are one separable Banach spaces. A is missing here. Are separable Banach spaces. So this is a kind of brief recollection of Banach spaces. I also have to mention that I take the category of Banach spaces and all bounded linear maps. So not only those maps having norms smaller or equal to 1, but having arbitrary norm. So this category looks more natural, but it's not nice. I haven't thought about that, but certainly it's not locally presentable, this category. But why I'm mentioning that? Because this category is again symmetric monoidal closed. And the tensor is so-called projective tensor product, well known from Banach space theory. And again, this A is missing here. And internal home is Banach space of bounded linear maps. So this is why I mentioned this category, because tensors in Banach spaces, you see, I want to know that Banach spaces have epsilon pushouts, basically. So there are various ways how to do it, but just I use this categorical way. So I will show that this category of Banach spaces, now usual ones, have tensors. So the tensor is projective tensor product of free Banach space over N and K. So this tensor is projective tensor in this category. And cotensors is internal home in this category, these bounded maps, again, of free Banach space over N is K. Yes, so this category of Banach spaces has weighted limits and colimits. So it has epsilon pushouts, even co-isometric epsilon pushouts and epsilon pullbacks, isometric epsilon pullbacks. One could also do it directly, and epsilon pushout, you can compare with metric spaces. You take a product in Banach spaces, which is in fact a product. Yes, I mean, it's Cartesian product, but you have different norm here. So you take a coproduct here, but now you change the norm of a coproduct, and you take norm generated by this condition. You see that's like if you want to identify FA and GA. So you want that FA minus GA is equal, so have norm 0. But now for epsilon to push out, you need the norm of those is epsilon multiplied norm of that. So that's, in fact, this epsilon push out, not using this name, but this construction is known with Banach spaces. Maybe not in the general situation, but in a special situation when one of these maps is identity. But you can, in fact, describe in this way that Banach spaces are epsilon pushouts. So you could have another way to prove that this category has weighted limits and colimits just by taking epsilon pushouts and epsilon pullbacks.
Jiri?
Yes?
Can I just comment? So in an enriched category, if you have cotensors, if you have a colimit which satisfies the underlying bijection of sets, it automatically gives you an isomorphism in the category. So I think, for example, that would mean that if you have one of these enriched categories which has cotensors, then epsilon pushouts are automatically co-isometric or something like that. Does that sound right?
I'm not sure, but I should think about that. Yes.
Mm-hmm. Okay.
So again, if you have tensors and epsilon pushout.
If you have cotensors, so you use the limits actually.
No, I think that's true. Yes.
Yeah.
Yes, I think that's true. Maybe it's also somewhere in our paper. Yes.
Okay.
Mm-hmm. So now this is the basic thing which one would expect, and what one would wish, that finite dimensional Banach spaces are approximately RF0 small with respect to isometries. So it means that they say behave like finitely generated, I could say. In category theory and objectively finitely generated, if you take a directed colimit of monos, so then this home functor preserves the colimit of monos. So here I would like to say that this home functor, this finite dimensional Banach space, preserves directed colimits of isometries, which is true, but that's in a weaker situation, but for the equivalent is there. So that looks something which should be true. And in fact, in that my paper with Walter Toll just we stated it just as triviality. But that's not triviality. And at some moment, this Jörg Adam, we started to doubt that it's true, but it's true. But I also have to acknowledge, you see, the problem is that simply somebody like me is not trained to write with Banach spaces, so that's the main obstacle. So really, we need some consultations from Vyacheslav Kubis, who somewhat helped us to understand this is true. On the other hand, this thing was never stated as such, yes, which in some sense, and probably Ivan will talk about that the next seminar, that it makes this category of Banach spaces something like enriched RF0 generated category. Because these things are enriched RF0 presentable, and any Banach space is just a directed union of finite dimensional subspaces. So, but this is the basic thing, because one just needs it to stop this approximate Soviet argument. So now this is the definition which just I started to mention at the beginning. So Banach space is approximately RF0 saturated. If it's approximately injected, if the isometries between finite dimensional Banach spaces in the category of Banach space isometries. So this is this formulation that I take injectivity to isometries. So I take those morphisms, G as isometries, but I want that these extensions are isometries. So just I say that this just everything is in isometries. You see, this is really distinction between injective and saturated, because that's not automatic that this extension is injective or isometric, and that's not always true. Yes, so this is this definition. Again, I see people doing Banach theory doesn't use this terminology, but they have different names for this. And now this is this main result, yes, that there is a unique up to isomorphism separable Banach space, which is approximately RF0 saturated. So that's known, yes, but I will connect it with known things. But just now what we want to do is to get it, say, to put it to category serial context, to enrich category serial context. So existence, this is what is theorem 1, because one does this approximate argument and it stops it at separable because these spaces are RF0 small. So existence is that theorem 1 which told you that these approximate injectives are reflective, bit reflective, and bit reflection is this approximate cellular thing. But unicity, this is much harder. I will mention it in a moment, yes. So how one usually proves the unicity? So usually one has two such saturated objects, express them as a colimit, in our case, a union of finite dimensional subspaces. Since they are separable, so this is a really countable union. So this is the colimit of those. One starts from the same thing to make this construction easy to formalize. And I have this connecting isometries here and here. Yeah, so I express K and L in this way. Now, since this L is actually isosaturated, so that's isometry from K1 to L. Why? Because I go from K0 to L, K0 is just 0, and just I use this approximate saturation to get this extension. That's not extension, but silent extension, but it's an isometry, like in the usual situation. And since it goes to L, so then I can factorize to something going to some L sub J up to some epsilon. So that's like in usual thing. But now I want to iterate it because I would like to have this G from Lj to K and extend it again from Lj plus 1. But for that, I would need this induced thing, which I get is an isometry. But isometries are not less cancelable. So I know that this G after something is an isometry, but it comes up to epsilon. So I don't need an isometry. So here, this construction somewhat fails. I cannot do it just with isometries because doing this usual back and forth argument, I would come to something which is not isometric. And I cannot continue with this construction. So what's the cure? The cure is that I define epsilon isometry, and this is precisely what you get. So something epsilon isometry, if you can complete it to isometries up to epsilon. This is exactly what we obtained there. This G is epsilon isometry here, not isometry. Yeah, because that's all obtained from injectivity. Yes, this is. Sorry, just when I was explaining to you, so I made a mistake because I should speak not about G but about F0. This is this factorization we get. Yes, I need this to be an isometry because then I would like to use this injectivity because I have from K1 to K, so I would like to get it from Lj to K. You see, maybe I should put it more explicitly in tag here, but I go from K1 to L by injectivity. And now I want to go from this L here again to K. I want to do it that just I take this one to K, so I extend it. But for that I need this isometry, but it's not, it's only epsilon isometry. Yes, so this is why this usual construction is raised. But it's isometry because just this is this situation. So now we came to another thing, which is in fact, this definition is not only balance spaces, this definition is an enriched category. And in balance space, these isometries are well known and they're called isometries. And it just means I formulated because morphisms are linear contractions. So it means that this difference between A and this contracted thing is not bigger than epsilon on elements from the unit ball. Otherwise, it wouldn't make any sense. Yeah, so this is epsilon isometric balance spaces. And now the key observation is that something is isometry if it's epsilon push out along identity is an isometry. It's in fact easy thing, yes, to check it. So in some sense, you having epsilon isometry, you can, by epsilon push out, you can improve it to isometry. And now, finite dimensional balance spaces are closed on epsilon push outs. This was this description here. Yes, because if these two things are finite dimensional, So also this is finite dimensional. Only I change the norm. There are many non-equivalent norms on finite dimensional spaces. So which means that in this way I can take this C, this improving to the finite dimensional, and using this I can extend this F0, which is bad, to something which is good, and use injectivity to good to get factorization from this bad. So again, I can extend this bad thing to good thing, but again to finite dimensional and isometry. And that can be extended because this case approximately injective, and I get extension of this. So this is how to somewhat solve this problem, this epsilon isometries appearing in the construction. And then one can run this back and forth. This is, in fact, it's a little bit more delicate because here I gave you only some of the basic idea how to overcome this problem, this epsilon isometries emerging in the construction. But one has to be quite careful because you have to increase those epsilon used to factorize, and also you have to decrease this epsilon for epsilon isometries because everything should converge to something. It should converge to isomorphism between K and L. So this is more delicate, but we can get theorem 3. And there's a little bit of history. Gurari constructed space in 1965, but its unicity, this is what I was talking about now, was open for some time, and it was proved by Lusky in 76 using D-bar space theory. And then Kubist and Soletsky gave an elementary proof quite recently. And in fact, what I explained to you is their proof, but just it's put to category theory framework. So everything what I did, in fact, they did it a little bit in different formulations. But this motivating fact that finite dimensional Banach spaces are approximately Alex-Zero generated, so that's not there. Yes, so this is an application that you prove with known thing, not new thing. Yes, how to use this enriched category theory for explain injectivity. So in the last couple of minutes, so let me to tell you something which goes beyond that paper with Ilka Adamek, and this that you look at the category of morphisms of Banach spaces. So objects are morphisms in Banach spaces. In fact, it's a category of operators on Banach spaces. And Garburicka, Vegžin, and Kubis found, again, analogy of Gurari space in this situation. So this approximate isosaturated operator on Banach spaces. Then it's easy to see that if you have this operator, so then both K1 and K plus separable and both are Gurari, so they're isometric. So in fact, this operator is an operator on the Gurari space, not between. So one could also look at it, but now it doesn't seem that operators between finite Banach spaces, that they are approximately or small isometries. I don't think that it's true, but they behave well with respect to maybe not all transfinite compositions of isometries, but to those which you use to construct this approximately saturated thing. So you still can do it, not by the same thing as before, but you can modify it a little bit, again, to give some kind of category theory understanding of what they did. The point is that if you play this game, you take those epsilon factorizations. So now you don't make spaces are these morphismal spaces. If you take some colimit spaces, so you take a morphism to colimit, you factorize it up to epsilon, but then the situation, the square you get doesn't commute, but only up to epsilon. So you don't get morphisms between morphisms, but you get just epsilon morphisms between morphisms. And you have to correct it. you have to correct by epsilon push-outs, and this correction is such that it still keeps in this constructions giving this approximate injective thing. So it's much more delicate, but it works, yes. Of course, one could come other thing, but here, and to come to Banach algebras, it means these are Banach spaces, this multiplication. So, and again, one has fine dimensional Banach algebras. So, question is, are there approximately LS0 small zero isometries? You see, this is the same, like you take Banach spaces and you take two sorted unary operation on them. This is this morphism. Here, instead of a two sorted unary operation, you take multiplication, which in fact here should be morphism from tensor product of Banach spaces to Banach space. So it's not kind of prop, yes, here, this Banach algebras. And so again, if you do it, so then you get problems with that it's the total morphism of prop not only up to epsilon, but this situation is totally unclear. And so this, I don't know. I can only show that if you take free Banach algebras over finite Banach spaces, so then they are LS0 small, but that's too few. Among Banach algebras, you have system algebras, which has special Banach algebras. So again, the same questions appear here, whether you can apply this theory to this situation. But that nothing nice classically about Burari system algebra. So this is not probable that one could do the same thing there. Yes, that's all. Thank you.
Okay, so thanks very much to Jiri, and we have our usual sound round of applause. So if anyone has any questions, feel free to unmute yourself and ask the question.
Yeah, I have a very plain and naive question though. Just in the first half, you have been dancing around what look like model categorical notions. Is there, after all, some strict or approximate version of a model category there?
You see, that's of course that's question because we were this Jirka, we are very pragmatic and we just injectivity. Because of course, then the question is there something like approximate weak partition system? And then the question is so yes. So this is tempting, but I don't know, and we haven't looked at that. Yes. Mm-hmm. But then really one should look at how to say at epsilon lifting properties. It's clear what one has to do. And these things can be also formulated in enriched categories theoretically. So there should be something, but I don't know. That's something which one probably has to look at, but it's unclear whether it's useful or not. I don't know.
Maybe one question, it's probably a silly question, but so you sort of define the approximate injectives in terms of the co-isometries?
Yeah. And
the co-isometries are the left class of a factorization system, is that right?
Yes. They are. Yes, they are like they are left part of strict factorial system. Yeah. Yes.
And are they occasionally they're probably not the right class of a weak factorization system as well? I was just thinking, if I remember your paper with Steve Lack, where you develop some of these things in a general context, I think it can be helpful if the class of morphisms which you're considering has some nice properties. For example, often one considers the surjections or the surjective equivalences, and these things are often the right class of a weak factorization system, so stable under pullback and things like that. But I don't know if
You see these isometries, if you take just usual categories as trivially enriched. So those isometries play the role of atoms.
Mm-hmm.
So in fact, this kind of atom injectivity somewhat just goes to usual injectivity on usual categories if you enrich them trivially. So this is, in some sense, quite a natural thing, yes, to take this.
Mm-hmm.
I don't know whether that could be also something big there. I don't know.
Okay.
And also this gain up to epsilon, you see, because for instance, some of those epsilon pushouts I use with identities. It reminds you to homotopy pushout along identities, which are not pushout, but they give path object or something, if I remember. Yeah. So that's this analogy is not totally stupid, yeah, but totally different because yeah, that's likely if you have that proper scale of homotopy index by epsilon. So I don't know that it makes sense.
Mm-hmm.
Jirka,
Yeah.
you mentioned in passing that the forgetful functor from Banach spaces to metric spaces preserves directed colimits. Is it true?
Yes, I believe that it is. If my proof is correct, yes.
Okay.
To complementary spaces.
Ach so, I thought you said to metric spaces.
So then that was not. So that was
Okay.
that's not possible. No, you are right. You are right. So that was just that. Yes. One should go to complete. Yes.
Okay.
I think yes. Mm-hmm.
Any further questions? Well, if not, let's thank Jiri again for a very nice talk. Okay, and so we can stop recording.